So today we're continuing talking about radian and degree measurement. Last time we were talking about coterminal angles. We're looking at a new pair of angles, which are the complementary pair and the supplementary pair. And we're doing them in degrees, but also in radians as well. So here's a little diagram to remind you that if you have a right angle, you've got perpendicular lines, and of course that's a 90-degree angle, so that would be a complementary pair. And if we're talking about a radian measure, then that would be two angles that add up to a total of pi over 2 radians. And if you have a supplementary pair, that's your 180 degree. And of course, that means you add them up to pi in radians. So there it is in the box. We're going to take the two angles, add them up to pi over 2, or up to pi, depending on complement or supplement. So we're going to be finding each of those. Here's some examples with degrees, and here's some examples with radians. So let's go ahead and take a look at number 4. So here we have 45-degree angle. Here's our complementary pair and the supplementary pair as well. We're going to find each of those. So we take that given angle of 45 degrees, we add it with its complement. Now we have a variety of variables we can use. We can use theta. Here in this, it's presented as using beta. We could really use any of those variables, so I'll just be consistent and use that beta symbol. They will add up to 90 degrees, right? And of course you have to subtract away the given angle to isolate your variable. So 90 take away 45. Here you have 45 degrees plus your variable beta, and for the supplementary pair you want to add them up to 180 degrees, right? So what we're doing to isolate the variable is subtract away the 45. Right? You've done that before, that's nothing really new. Here in the next example we have 103 degrees. So think about this for a moment. 103 plus what would add up to 90 degrees? Well, 103 is bigger, so there is no comp. Right? There's no complementary angle that exists because you have to have two acute angles that add up to 90 degrees, and technically that's an obtuse angle, so that won't work. But we do have a supplement. Right, so we take our given angle of 103, add it to the variable beta, and that has to add up to 180. So we're going to subtract that away to isolate the variable. So 77 is the result. It's a little trickier when we get to the next example because now we have a fraction to consider, but it's the same concept. We're going to take the given angle. Here's my complementary pair. Take the given angle. We have 2/5 pi. We're going to add that up to beta, and they will add up to pi over 2 radians. So we have to subtract away the 2/5 pi to isolate the variable. So that means beta is going to be found by taking the pi over 2, and we're subtracting away that 2/5 pi. Now, we need a common denominator, so multiply by 5/5 on the pi halves and by 2 over 2 on the 2/5 pi. So what that means for us is now we have a common denominator of 10. So you have 5 pi over 10 minus 4 pi over 10, so that'll give you 1 pi over 10. There's your final answer. Right? So notice that if we have an angle measure in terms of pi, we want our answer to also be in terms of pi. So no decimals here, we're just working with the fractions. For the supplementary angle pair, we take our given angle of 2/5 pi, add it to the beta, and that has to sum up to pi radians. So to isolate the variable, we have to subtract away the 2/5 pi. So you have pi minus the 2/5 pi. And once again, we have different denominators. So multiply your pi by 5/5. So 5/5 pi minus 2/5 pi will give you 3/5 pi. So there's the complement and the supplement. Now in the next example, this is also in radians. Right? You might not recognize it without the pi symbol, but there's no degree symbol, so it's not degrees, it's definitely radians. Because we have a decimal value, then we'll use our calculator and we'll get a decimal for the answer as well. So here's our setup for the complementary angle. 1.3 radians plus the beta has to add up to pi over 2 radians. Isolate your variable by subtracting away the 1.3. So pi over 2 minus 1.3. That's actually the exact answer, right? If we keep it in terms of pi, that would be the precise answer. But if we were to turn that into a decimal value by using our calculator, of course, it's now an approximate answer. But we're doing this in this section because if they are giving us a decimal in the problem, we'll use a decimal value in the answer, meaning we're keeping the same form. So if it's in terms of pi, we'll keep the pi. If it's a decimal, we'll just keep the decimal. So there it is. For the supplement, 1.3 radians plus beta adds up to pi radians. So isolate the variable. We're subtracting away the 1.3 from both sides. So there's the exact answer. And my calculator tells me the decimal value is about 1.842. So those are the two that are a little bit harder for us, just in the sense that we're using radians instead of degrees, and fractions especially. So pay close attention to those two examples. That's topic number 1. Next, we're talking about converting back and forth between radians and degrees. And we're doing that so that we can work with problems involving arc length. That'll be our third topic. We're looking at some, I call them landmarks. These are common angle measures that we may be familiar with. Actually, start here at this sort of bottom right corner and work your way back up again. So you know 1 revolution around is 360 degrees, and that's also 2 pi radians. We would normally put that information here where the terminal side of the angle is, but they actually printed it here on the bottom for whatever reason. So we know 360 is equivalent to 2 pi. We've got that memorized, so we can convert between one and the other just in our heads. Half of a revolution is pi radians, which is also 180 degrees. Again, they printed that information here on the bottom. A quarter of a revolution would be a fourth of 360, which is the 90-degree angle. And, of course, a quarter of 2 pi is half of a pi, so there it is printed at the bottom. So we've seen these already. We haven't officially introduced the unit circle yet. When we get to that, we'll be seeing these angles a lot more often. But here's your 60-degree angle, which is a third of that half at the top. That means we're taking this pi radians and dividing that into 3 equal parts. So that's 1/3 of a pi in radians. Here this is 4 equal parts, so this is 1/4 of a pi. And here this is 6 equal parts, so that's 1/6 of a pi. So that's why we call this pi over 6, and that's 30 degrees. So those we'll be memorizing. For any other angle that might be in between these common angle measures, well, we need a process, and this will be our process. This is what we'll multiply by. So if we're starting with degrees, and we want to convert with radians, we want to put degrees on the bottom so the degrees cancel out. And we're using pi and 180 as the conversion factor. So take a look at this next example. We have 120 degrees. Analyze the units. We have degrees. Set up your multiplier. We want the degrees to cancel out, so you have to put the degrees on the bottom, right? So 1 on the top, 1 on the bottom. That means you need radians on the top. So that means you want pi and radians on the top and 180 degrees on the bottom. So degrees cancels out with degrees. That's why our answer will be in radians. 120 pi over 180. Yeah, we should reduce that fraction. We can divide top and bottom by a factor of 10. So now you have 12 over 18. And we can continue to divide even further. And we'll turn that into a 2/3 pi. That's also one of our key angles. We'll be seeing that in the future when we get to our unit circle. Let's take a look at 315 degrees. Setting up your conversion factor, you want degrees on the bottom, so they cancel out with the degrees there. We want to turn this into radians, so again, we want pi radians on the top and 180 degrees on the bottom. So degrees cancel out. You have 315 pi over 180. Again, we want to reduce the fraction, try to keep this in terms of pi. So eventually we'll reduce it down to 7/4 pi. So let's go the other way around. Let's say we are starting off with an angle in radians, and let's convert that to degrees. So pi over 9 is currently in radians. So we want to set up our multiplier where radians is on the bottom, and degrees then will be on the top. So we want pi on the bottom and 180 on the top. Here, the radians cancel out, so that means we'll have an answer in degrees. But you notice something else cancels out. We have a pi above and below the division bar, so the pi over pi also cancels out, making this a pretty straightforward problem with 180 degrees over 9. So 20 degrees is that one. Take a look at this next example. We have 0.8. Notice there's no degree symbol. That means this is still a measurement in radians. So when we set up our multiplier, we want radians on the bottom. That means we want the pi radians on the bottom and 180 degrees on the top. So the radians will cancel out, But notice the pi symbol doesn't cancel out because we didn't have an angle in terms of pi to begin with, the way we did with the previous example. So that means we are actually just going to go straight to our calculator and get a decimal value. So if the problem has a decimal value, we'll use a decimal answer. If the problem is in terms of pi, we'll just work to see if we can either keep it in terms of pi, or in this case, the pi's do cancel out. So my calculator is doing all the heavy lifting here, 45.837, and that's in degrees. So we need those conversions to be able to solve the questions involving arc length. So let's turn the page and take a look at a couple at the top of the next page. This is our topic number 3. So we have seen this formula before. S is the arc length, and that is equal to the radius times the theta. The theta is your central angle measure. Here you have a diagram. There's your arc length. So, right, so it's a length. It's just a curved length, but it's a portion of the circumference. And if you are talking about the area of a sector, there's even a formula for that as well. We're not using this in our notes and in our homework. We won't be quizzing on it. It's just here in case you're curious about it. So there it is. We're just focusing on this formula only. So this is the one you need to know. So this only works if your central angle is in radians. Okay, so if they give us a central angle that's in degrees, well, we first have to convert back to radians before we can calculate the arc length. And that's what we see here in problem 10. Here's our example. We have a circle with a radius of 4, that's in inches. We want to find the length of the arc, so that will also be in inches. And this arc is intercepted by a central angle of 240 degrees. So if we illustrate that with this picture, we're trying to fit this in here. Remember, 180 degrees would be straight across, so I'm estimating something like that. That's your 240 degrees. So there's your central angle of 240 degrees. There's your radius of 4 inches. And we're trying to find how long is this distance as we wrap it around the circle. That's the S. That's the arc length. So step number 1, we have to convert the 240 degrees to radians. So this will be our theta. So we're starting off with an angle of 240 degrees. Set up your multiplier. We want degrees on the bottom so the units cancel out. So that's 180 on the bottom, and we want pi radians on the top. So unlike the previous examples where we were reducing the fractions, here we are not reducing the fractions. We're going straight to a decimal value. And part of the reason for that is because when we're talking about a length, well, think of it like a story problem, if you will. We'll just go to a lot of decimal points here, 4.189, and that's in radians. We could, reduce this fraction and keep it in its precise value, but as we have to plug it back into this formula to calculate the arc length, we want to know how many inches that is. So like I said, think of it like a story problem. We'll just go to a decimal answer. Now that we have an angle in radians, we can find the arc length. So that is S equals the radius times the theta. Okay, S is what we have to find. The radius is 4 inches. And our central angle is the 4.189. Now, because S is a length, that means the final answer has to have units that represent length. So the final answer is not in radians, the final answer will be in inches. So, again, multiply that together. Final answer is 16.756, and that's in inches because that's a length. That's the distance around that circle. Now, I found it helpful to do one more example of this type, so I'm going to go back up and use this space in the top half here. So we'll call this example 10 part B. All right, and we're just setting up a different situation. So in this case, let's find theta. The first example we did, we had to find the arc length S. Now we're going to go backwards. Let's find that central angle. So that means we have a circle where we already know the arc length. So this is the given information. Let's say that the arc length is 20 centimeters, and let's say the radius is 8 centimeters, okay? Those are both measurements of length. So if we were to draw a picture to illustrate this, we have no clue how big that angle is. We know we have a radius of 8 centimeters. And if we measure this distance around the circle from one radius to the next radius, that is our 20 centimeters of length around the curve. So S equals r times theta. S is 20 centimeters. R is also 8 centimeters. There's the theta. We want to get theta by itself. We're dividing both sides by not just the 8, but the 8 centimeters, because part of this is analyzing what's happening with the units. Right, so we'll take care of the 20 divided by 8 in a moment, but notice you have centimeters that cancels out with centimeters. It looks like you don't have any units remaining, but as we're measuring an angle, what that means is we are going to end up with a measurement in radians. So 20 divided by 8 is 2.5, and that's not centimeters anymore, it's radians, because that's the central angle. We're not doing the other examples down there. You see examples 11 and 12. We don't have any homework problems based on those, so we'll just stop right here.